Hello students, in this lecture I shall explain topic of vector spaces, which is a subject of linear algebra. The topic of vector spaces includes vector space, span of a set, linear dependence and independence, basis and dimension of a vector space, inner product and Gram-Schmidt process. Let us start. Vector spaces. A vector space, also known as linear space, is a set of objects called vectors. Vectors may be added together and multiplied by numbers called scalars. Scalars are often taken to be real numbers, but vectors may be multiplied by complex numbers, rational numbers, or generally any field. To specify that the scalars are real or complex numbers, the terms real vector space and complex vector space are often used. Euclidean vector space. In mathematics, physics, and engineering, a Euclidean vector, or also known as simply a vector, geometric vector, or spatial vector, is a geometric object that has magnitude and direction. A Euclidean vector is frequently represented by a ray, that is a directed line segment, or as an arrow connecting an initial point A with a terminal point B and is denoted by A with a right arrow. The magnitude of vector is the distance between the 2 points, and direction refers to the direction of displacement from A to B, which is shown in the figure. A is the starting point and B is the terminal point. In pure mathematics, a vector is defined as any element of a vector space. In this context, vectors are abstract entities which may or may not have a magnitude. Geometric entities having magnitude and direction are a special kind of vectors. They are elements of a special kind of vector space called Euclidean vector space. These vectors are sometimes referred to as geometric, spatial, or Euclidean vectors. Subspace. A subspace is a vector space that is entirely contained within another vector space. As a subspace is defined relative to containing space, both are necessary to fully define one. Let V be a vector space. W is said to be a subspace of V if W is a subset of V and the following hold. If W1 and W2 are elements of W, then W1 plus W2 are also elements of W. For any scalar C, if W is an element of W, then CW is also element of W. Span of a set. Span of a set S of vectors denoted by span S, that is S within parentheses, is the smallest linear subspace that contains the set, or as the linear combinations of elements of S. The linear span of a set of vectors is therefore a vector space. For expressing that a vector space V is a span of a set S, the following phrases are commonly used. S spans V, S generates V, V is spanned by S is a spanning set of V, S is a generating set of V. Given a vector space V over a field K, the span of a set S of vector is defined to be the intersection W of all subspaces of V that contain S. W is referred to as the subspace spanned by S or by the vectors in S, or S is called a spanning set of W. Alternatively, the span of S may be defined as the set of all finite linear combinations of elements, that is, vectors of S. Fundamental subspaces. The fundamental subspaces are four vector spaces defined by a given M cross N matrix A and its transpose. Number 1, the column space of A. Number 2, null space or kernel of A. Third, the column space of A transpose, also called the row space of A, and the null space of A transpose, also called the left null space of A transpose. The fundamental subspaces are useful for a number of linear algebra applications, including rank of a matrix. Column space. The column space of a matrix A is the vector space formed by the columns of A, meaning all linear combinations of the columns of A. Consider the matrix. Here A is the matrix and there are 4 columns. Then the column vectors are. Now please note that the third column can be obtained from the first by multiplying by 3, and the fourth column can be obtained by adding first and second columns. Therefore, third and fourth columns are not linearly independent, which form a vector space that has a basis of first 2 columns. As there are 2 vectors in this basis, the dimension of the column space is 2. Hence, the rank of A is 2. Null space. The null space or kernel of a matrix A, denoted by ker A, is the set of all vectors X for which Ax is equal to 0. If X and Y are in the null space, then C1x plus C2y is also in the null space, because A into C1x plus C2y is equal to C1ax plus C2ay is equal to 0. Row space and left null space. The row space and left null space are defined as the column space and null space of A transpose. In this way, they are subspaces of Rn, that is, n is the number of rows. Linear independence. Linear independence is a property of sets of vectors that tells whether or not any of the vectors can be expressed in other vectors or any scalars. Linear dependence. A set S is known as linearly dependent if one of its elements is a linear combination of its other elements. Basis and dimension. Basis. Let V be a vector space and S is equal to V1 up to Vk. B is subset of V. Then S is a basis for V if the following two statements are true. S spans V. S is a linearly independent set of vectors in V. Dimension. The dimension of a vector space V is the number of vectors in a basis. If there is no finite basis, then V is called an infinite dimensional vector space. Otherwise, V is a finite vector space. Inner product. The inner product is an algebraic operation that takes vectors of equal length and computes a single number, a scalar. That is the result is the scalar. The inner product is a generalization of the dot product that is specific to the field of real numbers. The inner product is a structure that generalizes to vector spaces of any dimension. Common example of inner product is force into displacement is equal to work, which is a scalar quantity. An inner product on a real vector space V is a function that associates a real number uv, that is within angle brackets, with each pair of vectors u and v in such a way that the following axioms are satisfied for all vectors uv and w in V and all scalars k. uv is equal to vu, that is the position can be interchanged. U plus v and w is equal to uv plus vw. Kuv is equal to k uv. U and u is greater than or equal to 0 and u is equal to 0 if and only if u is equal to 0. A real vector space with an inner product is called a real inner product space. Orthogonal basis. An orthogonal basis for an inner product space V is a basis for V whose vectors are mutually orthogonal, that is perpendicular. If vectors of an orthogonal basis are normalized, the resulting basis is an orthonormal basis. In functional analysis, an orthogonal basis is any basis obtained from an orthonormal basis using multiplication by non-zero scalars. Gram-Schmidt process. Gram-Schmidt process is a method of orthonormalizing a set of vectors in an inner product space, most commonly the Euclidean Rn equipped with the standard inner product. The Gram-Schmidt process takes a finite, linearly independent set of v vectors S is equal to v1 up to vk for k is less than or equal to n and generate an orthogonal set S dash is equal to u1 up to uk that spans the same k-dimensional subspace of Rn as S. Gram-Schmidt process of operation is a sequence of operations that allow to transform a set of linearly independent vectors into a set of orthonormal vectors that span the same space spanned by the original set. Two vectors R and S are said to be orthogonal if and only if their inner product is 0, that is, inner product of R and S are equal to 0. Given an inner product, the norm of a vector is defined as, that is, square root of product of S and S. A set of vectors is called orthonormal if only its elements have unit norm and are orthogonal to each other. Vectors of an orthonormal set are linearly independent.